I'm going to be talking about the Eoarchean and what's been going on for the last 50 years. But first of all, I really need to say thank you to my co-workers. I've of course had many co-workers over many years, but I particularly like to thank Clark Friend. We've been working together since 1976, so we've been working for 45 years. And then also Vicky Bennett in ANU, we've been working together for 32 years. So it's quite a long record. We've got obviously different ways of seeing things, different methodologies, but somehow we actually make a very long-lasting team. And of course, I should also thank all of the funding organizations. I won't go back into the last millennium, I'll stay in this century, and some of the organizations as shown along the bottom of the slide there. But I should particularly like to thank the University of Wollongong, the Australian Research Council, and the Australian University. So why 50 years of the Eoarchean? Well, actually, it is the 50-year anniversary of the first record of Eoarchean rocks surviving on Earth, and is shown as the cover of a reprint of the paper led by Lance Black. Lance Black at the time, he's Australian. He was a postdoc in the Oxford Isotope Laboratory. And in 1971, he was the lead of the paper presenting the first isotopic evidence for rocks dating from the Eoarchean. The Eoarchean, so obviously it's in the very deep past. So what is it? Some of you may not be fully aware. It's a slice of time which runs from 4,000 million to 3,600 million years ago. And there can be a little bit of a frustrating thing happening in that people think, oh, it's Eoarchean. That's a point in time. It's not a point in time, it's a long time. So the record of these Eoarchean rocks that we have in West Greenland, they actually cover 300 million years. So if you think of it in terms of the Phanerozoic, that's going from the permanent Carboniferous boundary up to now. And nobody in their right mind would regard every single rock you sample from the last 300 million years as equivalent. So it's a long time, and it's a long time ago. So over the years, there's been over the last 50 years, there's been other discoveries of Eoarchean rocks on Earth. However, even 50 years on, this West Greenland area around Nuuk, it still is really the key area. It's got about 3,000 kilometers squared of Eoarchean rocks, which are very superbly exposed, largely unweathered in a recently unglaciated terrain. And they form a tract which runs from the west coast inland ice margin somewhere around the Isua supercrustal belt, a famous locality I'll talk about, down to the coastal region, of which one place some of you may have heard about is an island called Eoikee. And just for a joke, I put on their red spot for my first field day in Greenland, 23rd of June, 1974. So I'm also heading for a 50-year anniversary of Greenland research. So very key area in the Eoarchean is this Isua area, which is up by the edge of the Greenland ice cap. It is a belt of, you've got the Isua belt, Isua supercrustal belt. It consists of 3,800 and 3,700 million-year-old volcanic and sedimentary rocks. And on the north side of that, you've got 3,700 granitic sensu lato rocks, whereas on the southern side, 3,800 ones. And running right through the center of that belt of volcanic and sedimentary rocks, you actually have a suture. So everything on the south is 100 million years older than the stuff on the northern side. At the other end, you get the Eoarchean rocks. They form an archipelago which disappear into the Davis Strait. And shown here is what has over the years been a very contentious locality, Eoikee Island, which is just a small part of that archipelago. So you've got this wonderful tract of about 3,000 square kilometers of really quite very well exposed, very old rocks to look at. So the discovery of the first discovery of Eoarchean rocks 50 years ago followed very, very shortly after the plate tectonics revolution. So immediately these rocks were discovered, the question started to be asked: was there some form of plate tectonics already operating in the Eoarchean, or was the lithosphere shaped by some entirely different process? In other words, some entirely non-uniformitarian process. And there I show the cover of a 1973 Royal Society meeting discussing early crustal evolution. This has been an ad nauseum debate ever since plate tectonics emerged, and it's certainly still just a hotter topic today as it was 50 years ago. And really a lot of the arguments or concepts haven't changed. So here I've got illustration from a paper by Chris Talbot in 1973 from that Royal Society publication, and it's a number for debate nowadays. So you've got two conflicting models at the top and bottom there, and that is the top one, a very non-uniformitarian one, is that early crustal evolution was entirely different from today, with essentially a static lid of lithosphere, which was evolving vertically and overturning with density instabilities. So for example, that could be McGregor 1951, or more recently, Webb 2020. At the other end of the spectrum, you have the idea that right from the very start, you are having lateral lithosphere motions in crustal evolution. And I show there sort of Talbot's preferred model at the bottom there, which I've added some red arrows on to indicate he was showing some form of convergent plate boundaries operating in the very deep past. Whether those were actually identical in form to modern convergent plate boundaries with singular subduction zones is, of course, a matter of debate, but essentially it's a division between lateral motions of the lithosphere very early on versus an idea of static lithosphere with vertical evolution. So it's a particularly difficult part of a geological record to reconstruct and interpret. Really, the first difficulty is how few rocks have actually survived from that distant time. So, of course, the constant motion of the plates, erosion from the surface, all these things over 3.6 billion years have played their had their toll on the early crust. So at the moment, you can probably say quite truly that only about 1/1,000,000th of the present crust is actually a rock surviving from the Eoarchean. So the main locality still really is Nuuk in Greenland, but there's other places which have turned up around the world over the last few decades. Particularly very important for us is the Naria area in Western Australia, but there's little bits and pieces dotted around all over the world. Anshan in northeast China is rather different. It's chosen not to be in a very remote place. In fact, there's some very nice outcrops of 3,800 million-year-old rocks by a park bench in the city of Anshan. So these little bits and pieces are all we have to understand the very early evolution of the planet. So we've got this tiny backyard of real estate, and there's so much disagreement concerning even the most fundamental question. So was there some form of plate tectonics, or should we say lateral lithosphere movements in the Eoarchean? And really, a lot of the difficulty in this comes not only from the very small amount of this ancient crust which survives, but also the state in which we find it in. And I think a very good analogy for it is this image of a housing estate in the US, which has had a tornado go through it. Most of it, all of the houses are flattened, complete mess. And that's a good analogy for most of the Eoarchean rock record, where you can get the broadest picture of the early Earth. So you can look at the bits and pieces and say, oh yes, this was obviously a housing estate, okay? However, just like all natural systems are naturally chaotic, you get the occasional fluke happening, as shown here by just one or two houses mysteriously still standing, where you can actually have a lot more information extracted because it hasn't been so much destroyed by later tectonothermal events. So something like this rare fluke of a house standing in this tornado area is a very good analog for the survival of rare Eoarchean details. And these, I would reckon, form much less than a trillionth of the present crust. Those areas forming much less than a trillionth are the ones which are providing us the most insight as to the nature of the early Earth and how it operated. So that's problem, this corruption. So this is a good example here. This is what typically the Eoarchean crustal remnants look like. They are really just a horrible mess of migmatite. Migmatite's just a posh word for mixed rock, dominated by broadly granitic rocks. So although the rocks here are Eoarchean in age, nearly all the features that you can see in them are actually being impressed on them in high-grade metamorphism and deformation towards the end of the Archean. Not recognizing how modified some of these things are can definitely lead to differing interpretations of geochemical and isotopic data, which probably a lot of nuances which I won't go into in this talk. However, what you have to do is really to find the very rare areas where you haven't had this terrible overprint destroying a lot of the original features. And finding these areas of little Neo-Archean deformation is where you can start to sort out some of the basic information about crustal evolution. So the Isua area up by Greenland ice is the best for this. Overall, it's escaped a lot of Neo-Archean deformation, even though it has a relatively mild lowermost amphibolite facies metamorphic overprint. So this is an example of extremely rare occurrence where there's absolutely no Neo-Archean deformation at all. And actually, when you come to look at these 3,650 million-year-old granite sheets, there isn't even any Eoarchean deformation, whereas the tonalites that they cut, slightly older tonalites at 3,700, they're weakly deformed. So you can just go follow these a few kilometers and the same rocks transform into these greater than 3,600 million-year-old mylonites, which are major early faults juxtaposing unrelated rocks. So even if you strip off these later tectonothermal events, you are still left with a very complicated Eoarchean history to unravel. A second corruption that you have to deal with is metamorphic reactions and variable degrees of open system behavior. They can radically change the appearance of the rocks, and they can also variably corrupt the geochemical fingerprints of the rock's origins. So I take as an example here something which again is a very contentious, still contentious set of outcrops. They are single discovery of original stromatolite structures found in 3,700 million-year-old silicious dollar stones. And the relic stromatolites are these bumps that you can see along these layers here. So in this particular case here, you can still see the structures quite well. Original lithologic layering in rocks where quartz and dolomite are actually in equilibrium. However, you can just go 10 meters from that, where you've had flux of water along grain boundaries to flush out supporting CO2 in these lithologies. And in that way, you are promoting a reaction of quartz plus dolomite giving you tremolite, and that just simply obliterates all of the fine details that one can see in the rock. So you go from something here, which has got this fine quartz plus dolomite layering, into this very coarse-grained tremolitic rock, which in a very superficial way actually even looks like a very messy basalt, even though its protolith was originally a silicious dollar stone. And to do this, all you have to do is, as I say, flush out a bit of CO2, add a bit of water, and you go across this reaction line here where dolomite and quartz are going to give you the tremolite. So all of these things work against us in interpreting the very old geological record. However, if one spends enough time plodding around the place, looking, doing detailed mapping of one's own, one does in the end come up with quite a good inventory of bits and pieces of fairly well preserved Eoarchean rocks, which give you a broad insight as to how crust was evolving. So amongst the inventory that we actually have small relics of Eoarchean mantle, which have got trapped in the Eoarchean crust. We've got volcanic rocks, which locally, very locally, are preserving pillow structures. We've got undeformed tonalites, very rare, completely undeformed. They represent, in our view, juvenile arc crust. We have got granites, typical two feldspar granites, biotite granites, and they're formed from the remelting of primary crust. And we even have very rarely preserved sedimentary structures. So this shows a very rare example of a breccia where the class consists of chert and fragments of andesite. And this is give you some idea, this is 3,700 million years old. So it's extraordinary that these sort of things have actually survived. So how do we find these gems? Well, along with my colleague Clark Friend, we have actually been undertaking systematic geological mapping in Greenland from the mid-70s onwards in a very old-fashioned way, plodding around mostly on our feet in the daytime, plus then doing old-fashioned inking in and compilation in the evening. So it's only by this sort of work that you can actually locate the localities of real scientific interest. And of course, that's only one side of the story. The other side of the story, as in any history, is you've got to actually have some ages to piece everything together. And the application of a shrimp iron microprobe for uranium lead dating has been a core and essential part of that. This has been going on now for several decades for the West Greenland rocks. A lot of the work was actually done on the now dismantled original Shrimp 1 instrument. This photograph here showing the original team led by Professor Compton and much younger Ian Williams over there. And this shows the instrument which I've mostly been using in recent years, which is ANU's Shrimp RG instrument, a third generation instrument. So why should we always go for this most expensive technique of dating? Well, one thing is that some of the rocks that we work on have got extraordinarily small zircon yields. So for example, I show down here an example of one of 4 or 5 very, very tiny volcanic zircons, volcanogenic grains, extracted from Isua banded iron formation, only 40 microns across, and you need a delicate technique in order to preserve these very rare grains for any other further studies. So that's a typical spot, 20 micron spot, which after finishing analysis is only 1 or 2 microns deep. So the integration and playoff of the field geology and the shrimp geochronology has been essential in piecing together the early Earth geological record. So let's return to the nub of the debate about was there some form of plate tectonics right back in those very distant times, or was there some entirely different form of lithosphere evolution? For example, this sort of stagnant lid vertical evolution model, which some would propose. So what I've done, I've chosen sort of 3 measures to see whether a plate tectonic style with lateral plate movement is actually viable from looking at the earliest record. So mantle rocks overlying crustal ones and older rocks overlying younger ones. I consider that this is certainly one thing that is much easier to achieve if you have lateral lithosphere motions with convergent boundaries than if you're looking at vertical evolution of the lithosphere. Another thing is something which would be in favor of a convergent plate boundary, lateral plate movement model, is if you can find packages of volcanic rocks where you've got no komatiites, but instead you have mafic and intermediate rocks with the geochemical signatures of fluid fluxing of the mantle, not adiabatic decompression of the mantle. And finally, something which I would also consider very definite in favor of some form of plate tectonic regime with convergent plate boundaries is if in the very oldest part of the geological record, you could find ultra high pressure metamorphism. So we'll look through these 3 things to look at the evidence that we can find. First of all, we'll look at older rocks tectonically overlying younger rocks. And again, we come to Isua, which is free of this, or largely free of this later tectonic reworking. And you can see some of the early structures, the Eoarchean structures, better preserved. So in this particular area up in the northeast part of the Isua supercrustal belt, one actually has got a set of refolded folds where you have got a set of isoclines which are wiggling here over a set of later closures. But the boundary here around this light green unit is actually a tectonic one, and it is meaning that you have got older rocks tectonically overlying younger rocks. So this pale green unit here is a unit of about 3,720 pillowed volcanic rocks, actually with a geochemical bonanitic affinity, and they're folding this folded frost sheet on top of younger rocks, which are about 3,700 sedimentary rocks, which themselves are actually unconformably overlying andesites of about this age. So this unconformity is most places even so obliterated and deformed, but there are a few places where one can actually make a very good case for an unconformity. For example, one can see pillows facing directly up into a set of dollar stones. You've got lenses of conglomerate along the contact as well. So if one unfolds all of this and reconstructs it and puts some of the geochronology on, this is the kind of story you get. Here we have the underlying bunch of, in this particular place, right up at the contact, pillowed andesites. The pillows face directly up into that contact there, and it's got a zircon age of about 3,710. Along that contact, we've got some conglomerates dominated by clasts of chert and andesite, but they still contain very rare detrital zircon, as do the package of silicious dollar stones, which they followed by, which also contain rare detrital zircon. You then go up into a package of banded iron formations and chert, and they have got, as I said, these very rare little volcanogenic zircons, which are essentially ashfall in origin, which are distinctly younger. You go over this tectonic contact, and then you're into the older bonanitic unit over the top. In one case, we've got a bonanitic gabbro giving an age of about 3,720, and as the youngest age limit in the rare low strain zone, we actually have a tonalite dike cutting them to give the youngest age of that unit. So this reconstruction is showing we have got older rocks tectonically overlying younger ones. So how about mantle rocks structurally overlying crustal rocks? Again, this would be best brought about in some kind of convergent tectonic situation. And here we go back away from Isua down to the coastal region to this area called the Gneissic Peninsula, where actually there is an ultramafic body. It's just large enough that you can see it from space 100 kilometers up. So there's a little sort of yellowish blob here, which is actually a little bit of Eoarchean mantle caught up within the Eoarchean crust. So most of the contact between the ultramafic rocks and the surrounding ones is unfortunately not exposed. However, along one section for not very far, maybe 20 meters or so, you can actually put 1 foot on the Eoarchean mantle and 1 foot on the Eoarchean upper crust. So these are all occurring in a syn form. So the dunites here are in the syn form, and they're wrapped around by these messy rocks of crustal origin. So you have these cherty, sort of rather iron-rich sedimentary rocks, and then we have skarny volcanic rocks here, which would have been very sort of messy, rather altered basalts prior to metamorphism. So here we actually have evidence of some mantle rocks overlying crustal rocks in the Eoarchean. So what sort of age constraints have we got? Well, first of all of this lot here are forming a large blob engulfed by tonalites of this age of greater than 3,750. But fortunately, at one locality in the Dunites, we actually have got a diorite dike cutting the Dunites, and that's got an age of 3,768. When you look at the mantle Dunites, they're actually quite nice because, of course, they're predominantly olivine, highly Magnesian olivine, but they've also got little bits of pargasite in with them as well, to show that they've actually had some fluid interaction sometime in their life. And you can actually see maybe some of the origins of this sort of fluid interaction, because this diorite dike, Eoarchean diorite dike, has actually got this quite impressive hornblende-rich reaction halo around it. So when you look at the diorites, in this case intruding the mantle dunite, you can actually see they have a classic trace element signature of fluid fluxing of the mantle wedge. So you have the typical negative titanium anomalies, you have the negative niobium tantalum anomalies. Also, you have the general, as you go from right to left across this diagram, overall enrichment of elements relative to primitive mantle. When you look at the ultramafics themselves, these are the two most recent samples we've had analyzed. There's a few more which cluster here as well. They have got classic geochemical signature, major element signature of depleted mantle, dunite and harsbergite. However, in with this body, plastered along the edge of this body, there are some layered gabbros, and associated with those layered gabbros, you do get some peridotites, which have got more the geochemical affinity of ultramafic cumulates from gabbroic magma. But this is by far the most abundant ultramafic geochemical type present at that locality. So we've got evidence of, in Isua, of older rocks thrust over younger ones. When we go down to this gneissic peninsula, we can make a case that you've had Eoarchean mantle has been emplaced on top of Eoarchean crustal rocks. Another thing that one can do using the metabasic rocks is look at their geochemical signatures. And one very interesting thing about the geochemical signatures of these rocks in West Greenland is that none of them have got the geochemical signatures of komatiites. Instead, all of them, all of the mafic and intermediate rocks, they've got the chemistry of formation by fluid fluxing, and they fall up here in the arc field. So just as an example, I've taken Isua 3720, 3710 million-year-old rocks, where we go from in the arc field from the bonanites down here through to rocks which are best described as island arc-foliites, and finally up here into andesites and diorites in the field there. But one could actually take any of the West Greenland suites. One could take the Isua 3800 ones. We can take the older ones with almost ages of sort of 3,870 around the Achillea area, and they all will fall up in this area here. To date, there have been no record of komatiites or morb-like rocks coming from the preserved record in West Greenland. The other thing that one could consider is ultra high pressure metamorphism. So where these are found, these rocks on in the Phanerozoic earth, they are indication of subduction system, and they're preserved by very rapid exhumation of such assemblages into the crust where they're trapped and preserved. So this is up to about 3,500 million years ago, a compilation of metamorphic conditions taken from Brown and Johnson 2018. I've played around with the diagram a bit so the scale varies along it, so that all of the Phanerozoic is just being compiled into one block. And then the time from the Cambrian through to the early Eoarchean is shown there, and then until the Eoarchean boundary is shown there, and then the space for the Eoarchean is shown over there. And what about metamorphic conditions here in the Eoarchean? So is there no record of these kind of very low geothermal gradient metamorphic assemblages, meaning that you didn't actually have any kind of subduction-like process going on, or is it they're just simply very rare in the geological record? So as you can see, even when you're getting into the Proterozoic, they are getting extremely rare. So it could always be a preservation thing, but of course people will also argue that there wasn't any form of plate tectonics in these times. You're not going to see that kind of metamorphic regime. So again, we're going to go to a different part of Isua, and this is our map of the northwestern end of the Isua supercrustal belt. You don't have time to take in all the nuances, but I'd just like to point out to you all of these stripes of different lithologies forming the belt here. A lot of the boundaries between these different lithologies are tectonic. Some of them are of unknown origin, but certainly a lot of them are tectonic. And note also the nature of the lithologies, all of more or less the same age. So we have got bonanites, we got things that are best described as sort of island arc foliites in their chemistry. One's got andesites, one's got andesitic greywacke, and one's got chert and banded iron formation, all about approximately 3,700 million years old. But most interestingly, as part of this tectonically intercalated assemblage here, and all the tectonic intercalation here is Eoarchean. It's very early, it's not related to much younger tectonic events, is this belt here of ultramafic rocks. So most of these ultramafic rocks are schistose. They can now contain a lot of amphibole, talc, and so on and so forth. But you actually got some nodules in there of considerable size. So this one here is about 100 meters across, this one several hundred meters across, where you have got relict olivine-rich assemblages preserved. And this photo here is a view looking over this particular body here, where we got the bonanites off to the west. We got this big lump here of ultramafic rocks, still with a lot of olivine in, and on the other side you got the sort of foliatic amphibolites. So let's actually have a look in detail at some of the metamorphic or assemblages that we find within these relics, which still got a lot of olivine preserved in them. So the predominant minerals in the relict assemblage is antigerite and olivine, very magnesian olivine, but with the olivine and the antigerite, one gets various titanium-rich phases. It's obviously a minor phase. These are very low titanium compositions. And the phases that you find are titanochondrodite and also titano-clinohumite. This is little chemical plot here is distinguishing some of the occurrences are titanochondrite, others are titanoclinohumite. So it's been found that if you have this assemblage, olivine, antigerite, and these titanoclinohumite, chondrodite mineral assemblages in these kind of lithologies, which have got mantle-like granitic compositions, very low titanium, that in order to actually have these phases stable, you need very, very high pressures. So in this particular phase diagram here, the transition from titanochondrodite to titanoclinohumite, if you have olivine and antigerite stable, is somewhere in the order of 2.5, 2.6 gigapascals. So in other words, one is definitely looking at preserved relics of ultra high pressure metamorphism, which have been trapped and brought up within these probably originally serpentinite melanges to be as little slivers and lenses between the bonanites, island arc foliites, and so on and so forth. So we think that we do actually have extremely rare occurrences showing Eoarchean ultra high pressure metamorphism. And to give you a sort of a scale of these kind of discoveries, that bit there is only about 40 microns across. All of these diagnostic mineral grains, they're in the order of 100 microns across or less. So actually, when one does look at the vestiges of the Eoarchean metamorphic record, we think that we have got these ultra high pressure assemblages, but also dotted around the place one actually finds different metamorphic assemblages recording different thermal conditions. So for example, we have got one example of high pressure granulites, which are very well dated from zircon. We've also got a more widespread occurrence of low pressure granulite, low pressure amphibolite during later migmatization events. So actually what we have is we actually have a broad range of metamorphic conditions on the early Earth in the crustal, preserved crustal record. But most importantly, it does look like we have very extremely rare occurrences of very old ultra high pressure metamorphism preserved. So how do we make juvenile crust? Well, on the basis of what I have presented, at least from the Greenland record, I would actually make a case that some form of convergent lithospheric movement is best to explain what we have. So I would imagine that this could be any time between 3.9 and 3.6 gigayears ago. You have lateral movements, you get the rupture of the oceanic crust, and then you get the fluxing of the upper mantle to generate these sort of island arc analogues, where you actually have got things where you can see you've been having fluid fluxing melting of ultramafic rocks. And then these sort of island arc analogues are not strictly island arcs, they're the analog for island arcs in those ancient times. They got trapped in very large volumes of tunnelite, which we know from the geochemistry was formed by the partial melting of eclogite. So one can imagine a scenario where you're having a continual crustal convergence, and what is happening to the underthrust, subducted underthrust, choose your words, crust is converting to eclogite, and then that is partially melting in order to give you the vast amounts of turnolite, which is swamping the earlier volcanosedimentary sequences. Finally, you do get crustal thickening, and it's interesting because the single occurrence of high pressure granulite that we've managed to date actually coincides with a time when tonalite genesis turns off and production of true granite turns on. So we have this early part of the history, Eoarchean history in West Greenland, from about 3,900 to about 3,660, where we have predominantly, for want of a better word, island arc-like sort of sequences swamped by tonalite. Then we have evidence of a high pressure metamorphic event. And then after that, one goes into crustal recycling, remelting of that somewhat older crust, generating crustally derived granites. Finally, life probably did change. And this will come on to something I want to talk about in the last one or two slides. When you get to somewhat younger times, we're leaving the Eoarchean now and going into the Paleoarchean, we're looking at places like the Eastern Pilbara, where there really is very good evidence of plume-driven processes modifying and creating new crust. So what I'd like to imagine is a scenario where something like the Paleoarchean in East Pilbara is sitting over a plume. This is a kind of model which is accepted and promoted by most of the people who work on the early Earth, whereas the crust that one sees preserved in West Greenland was formed by a completely different process. However, it is seeing some influence from this Paleoarchean event, basically a plume event. So when one looks at the Eoarchean rocks in West Greenland, they are cut by major suites of mafic dikes. The age of them actually coincide with the age of the oldest mafic crust formation in somewhere like East Pilbara. So most of these dikes are foliatic. However, there are some very more mafic ones, which a good interpretation of them could be that they actually represent komatiitic magmas, which have undergone some very wholesale incorporation of continental crust during their ascent in order to give some noritic compositions. So I always make a plea. Please don't mix up and equate Earth's Paleoarchean and Eoarchean geological records. So there's sort of a modern tendency at the moment to say, okay, if you look at someone like East Pilbara, you can actually see really a lot more of a geology. There's an amazing amount of detail if you go and look in the right places. You even get a course in rare occurrences, the oldest microfossils preserved. And there's a bit of a tendency with some people at the moment to say, okay, we understand how the Pilbara is working. On the other hand, places like the Eoarchean of West Greenland is really a terrible mess. Why don't we just apply the East Pilbara geological model to West Greenland? And I think that this obviously just simply doesn't work. It doesn't make any sense. And like I said before, when it even comes to looking at the Eoarchean record, just don't equate all of Earth's Eoarchean rocks, even within West Greenland. So in West Greenland, you've got the oldest rocks we found are just shy of 3,900 million years old. And then the youngest granites we have are about 3,600. So within that particular terrain, we've got 300 million years of history. And if you add on what I think is a rifting intrusion of the Emerilic dikes, you've got 400 million years of history. So you can't just take any old lump of the Eoarchean crust and compare it with another. You've got a vast amount of time and different processes going on. And just to give you an example of why one shouldn't equate things. So if you go to something like Isua, which some people can regard just as some monolithic entity. Oh, this is Isua. We'll take a sample of Isua. It'll tell us all about the early Earth. It doesn't matter exactly what we collect. It's just Isua, so that's good enough. However, if you actually look at Isua, it is, even by the end of the Eoarchean, it is incredibly complicated. The main division is the southern part of Isua, consists all of 3,800 volcanosedimentary rocks. But when you go and look in the northern part of the, step over the suture and look in the northern part of the Isua supercrustal belt, if you start piecing together all of the tectonic panels, there's an incredibly complicated history, and we can even identify some of the sources of components coming into some of the volcanic and volcanosedimentary rocks. So, takeaway message from the rare Eoarchean sample in Greenland. All samples of the early geological record are small and diverse, and it's really only very tiny areas providing the most detailed information. I would argue that Greenland's Eoarchean metamorphic rock record, integrated with rock types, actually basically fits more of a convergent plate boundary processes with collisional orogeny than looking at some kind of static lid scenario. However, it's very important to stress that I think ancient geodynamics had affinities with the modern plate tectonics plume dualism. And you can see that by comparing and contrasting the Isua Greenland Eoarchean record with what we see in the Eastern Pilbara. Therefore, I feel there's no need to invoke really unique non-uniformitarian theoretical scenarios to understand the early Eoarchean Earth. And just to finish off, perfect Isua day, why one always goes back. So here we are, a bunch of us looking at relics of Eoarchean, kyanite plus staurolite, Barrovian metamorphic assemblage. Okay, thank you very much. So I'm ready to take some questions.